We talked about the direct comparison test, and now we're going to move on to the limit comparison test. Now, these are similar to each other, but in that they're comparing series we know with series we don't, and comparing simple ones like p-series and geometric to things that aren't quite p-series or geometric. So here's what the theorem says. Suppose a and b in are greater than 0, so two sequences are greater than 0, are positive, and the limit as b, this should be n approaches infinity. Let me fix that. The limit as n approaches infinity of an over bn equals L, where L is finite and positive. Then the two series either both diverge or both converge. So let me try to interpret this for you. This time it does not matter which one's bigger or smaller, like it did with the direct comparison. We're just concerned that they're both positive. So we suppose that both of them are positive, and then what we do is we take them and we put them on top of each other in a big fraction. And it does not matter which one goes on top either. You can put either one on top. So you take the limit as n approaches infinity of one sequence over top of the other, and if when you take the limit you get a finite positive answer, then the series both do the same thing. So you should be comparing it with something you already know. So if the one you know converges, then they both converge. If the one you know diverges, then they both diverge. Now if you get a limit that's not finite and positive, that doesn't mean they do opposite things. That just means this doesn't work and you've got to try something else. Either compare it to something different or try a different type of test. So let's try 3 examples. First, we have the series 1 over 2n minus 3. Similar to the direct comparison test, you want to kind of strip this down to something you can compare it with, 1 over n. 1 over n diverges. It's a p-series that diverges. So here's what we're going to do. We're going to take the limit as n approaches infinity and put one of them over top of the other one. We'll take the limit, and if we get a finite positive answer, we know they both do the same thing. So we have a fraction over a fraction, so let's multiply by the reciprocal. Gives us 2n minus 3 over n. If you just remember the shortcut rules, the fact that the powers of n are the same on top and bottom tells us the limit would just be the coefficient, so we'd get 2 over 1 or 2. So since our answer is finite and positive, that proves that these two series do the same thing, which means that they both diverge. Okay, if you notice, we could have set this up the opposite way with 1 over 2n minus 3 on top originally. The only thing that would have changed is our answer would have been 1/2 instead of 2. Well, that's clearly still finite and positive, so it still would have worked. So it's up to you which one you put on top. Okay, when you're doing these, what is in general the best way to approach it is pick the most powerful term on the top. Well, in this case we only have one term, and the most powerful term on the bottom, n squared. Now that itself is not a familiar form. It's not anything we're familiar with. But if we rewrite this and then simplify it, suddenly it is familiar. It's a p-series that converges because the power is bigger than 1. So it converges. So now we're going to take the limit as n approaches infinity. Do 1 over n to the 3/2 over, I'm going to change this to n to the 1/2 over n squared plus 1. And when we are dividing two fractions, we need to multiply by the reciprocal. So on top we have n squared plus 1. On the bottom, n to the 3/2 times n to the 1/2 is n squared. So if you notice, again, the powers are the same on the top and the bottom, so we just use the coefficients, and our answer is 1. 1 is in fact finite and positive. So that means they both do the same thing, so they both converge. Okay, one more example, then I'm going to try to explain why this works and what we're really doing. Again, when you approach a problem for the limit comparison test, you want to keep the most powerful term on the top and the bottom. So the most powerful term on the top is the only term in this case, n times 2 raised to the n, and on the bottom I'm just going to keep n cubed. If you want to keep the 4, that's not going to cause a problem, but you don't need it. So pretty much drop any less powerful terms, any constants and coefficients. Okay, now just to be clear, n times 2 to the n is a single term. Since they're being multiplied together, they are one term, and you don't want to let go of any of that. Okay, so I can cancel out an n, and that gives me 2 to the n over n squared. Okay, now this is not a p-series or a geometric series. However, if we apply the nth term test here, if we take the limit as n approaches infinity of 2 to the n over n squared, 2 to the n is an exponential, and it's going to move faster than n squared on the bottom, which is a polynomial. So since the top moves faster than the bottom, we know the limit is going to be infinity. And the nth term test tells us that if the limit is anything other than, lost my train of thought. If the nth term test says if the limit is anything other than 0, there we go. If the limit's anything other than 0, then the series diverges. Okay, so now we know something similar to this diverges, and we'll compare it to it. Okay, one thing I'd encourage you to do, you can skip the step where you write one on top of the other, and just skip right to multiplying by the reciprocal. Again, which one you flip and which one you put on top is not important. It'll work either way. Alright, now if you notice, we can cancel out the 2 to the n. There's one on top and bottom. And we end up with 4n cubed plus 1 over n cubed. The powers are the same on the top and the bottom, so that means our limit is just the coefficients, which would be 4. 4 is finite and positive, so that means they both do the same thing. So they both diverge. So let me try to briefly explain why this works, what we're really doing. Right, if you think back to, I called it Tybo. The concept that basically if the top is moving faster, the limit is going to be infinity. If the bottom is moving faster, then the limit is going to be 0. And then if the powers were the same, or if they were moving the same speed, then you just got a coefficient, which is kind of what we're going for with the limit comparison. The limit comparison. We don't want 0 and we don't want infinity. We want a finite positive answer. And that's going to result when the top isn't bigger, the bottom isn't bigger, but they're the same. So when we get a finite positive answer, what that really tells us is that the top and the bottom of the fraction are both moving at approximately the same speed. Now obviously it may be off by a coefficient, that's why we get a coefficient, but in general they're moving at the same speed. One is not significantly faster or moving significantly differently than the other. So that's the idea. When we get a finite positive answer, it proves the two things are moving at a similar speed. And if they're moving at a similar speed, it would make sense that they would both either converge, if they were both getting smaller, going towards 0 and converging, or if they're getting bigger, they're going to both diverge, because they're going at the same basic speed. So if one diverges, the other is going the same speed, it must diverge also. If one converges, well, they're going about the same speed, so it must converge also. So that's the concept behind this. We're trying to prove that they move at about the same speed, and if they do, that tells us that they both do the same thing, and speaking as far as converging or diverging.